Hello, I'm AKM Mubashir Alam. I'm a PhD student at Marquette University in Computer Science Department. Today I'm going to present SGX MR, regulating data flows for protecting access patterns of data-intensive SGX applications. This research has been done by me, my PhD advisor, Dr. KK Chen, and one of his ex-PhD student, Dr. Sagar Sharma, who is currently affiliated with HP Incorporation. Cloud computing has become very popular because of its key benefits. For example, economics, the pay-as-you-use billing model is much cheaper compared to building your own infrastructure. The scalability, the plenty of resources out there for storage and computation compared to your local machine, for example, the personal computers, and also the accessibility, the easy access regardless of time and location. So in a cloud computing scenario, the user uploads the program and data to the cloud, and after computation with the given program and data, the results get back to the user. So when user upload the program and data to the cloud, the user actually losing the authority of the program and data, and the server owners actually hold all the authority of the data and the program. So if the server is malicious, they can temper the data, they can temper the program, they can even steal sensitive information. So to achieve the benefits of the cloud, user ultimately compromising the security and privacy. So the ultimate goal should be the confidentiality server, so that the server learns nothing about the program and data, to achieve integrity so that the server returns the accurate results from the cloud, and also to achieve the confidentiality and integrity, so the overhead should be much less, so the efficiency, the runtime, the execution time should be much faster. There are several existing solutions to address the issues. Researchers have been doing a great job. There are software-based cryptographic approaches such as fully homomorphic encryption and also the secure multi-party computation to address the confidentiality problem. But the problem is they are too expensive to be practical. On the other hand, there is trusted execution environment such as Intel SGX that overcomes the performance issues, and it also provides the both confidentiality and integrity guarantees. Intel SGX as trusted execution environment. So Intel extended their popular x86 instruction set to provide a private reserved memory where privileged system code such as the operating system, virtual machine, BIOS cannot access the private reserved memory. CPU itself restrict them to access the reserved memory where the rest of the memories can be easily accessed by the privileged code. So this security is actually provided by via remote attestation, as where the user get the guarantees that the service provider, the cloud service provider, actually providing the SGX supported CPUs, which actually guarantees this type of security. So in the scenario, user can upload their encrypted binary and the data, where using that binary, the enclave has been created on the cloud, and then they can securely transfer their encrypted data via the enclave call. And when the data is transferred to the enclave, then they are decrypting they will decrypt the data to work with the plain text environment. So the within the enclave memory, the reserved memory is actually working as a plain text so that the execution will be much faster than using the fully homomorphic encryption or the other cryptographic approaches. Intel SGX is secure to be deployed in a cloud server. However, it still has some privacy issues. Intel SGX is vulnerable from software-based attacks such as page fault attack, data or page access pattern attacks, and branch shadowing attack. In this research, we are going to focus on these software-based side channel attacks. However, on the other hand, there are other side channel attacks too, such as speculative execution attack or injection-based attacks. Since software-based mitigations are not sufficient or it may require microarchitectural level patches, we keep these side channels out of our scopes. So why still SGX applications are vulnerable from privacy and security issues? So we know that the operating system cannot access the application's trusted memory, or we can say the private reserved memory. But the problem is the physical trusted memory is limited to 95 megabyte. So for this reason, the application's data, the entire data set cannot be uploaded to the trusted memory. So the application needs to upload the limited data to the trusted memory on demand basis, and sometimes it may need to spill out the data from the trusted memory to untrusted memory. So these interaction between the trusted and untrusted memory can be detected by the operating system. And also there are other mechanisms like you can virtually increase the trusted memory, the size of the trusted memory. So in that case, the operating system itself will handle the paging mechanism to swap in and swap out the trusted memory to the enclave and outside of the enclave. So when the operating system get the authority to do that, operating system can observe the page level access patterns. So for these reasons, the memory trace can be detected by the operating systems. Speaking of the access pattern leakages, there are existing solutions for this problem. Oblivious RAM, or known as the ORAM, is very well known to protect the access pattern between a server and a client. So researchers have been experimenting ORAM to address the data access patterns of SGX applications. So in the SGX setting, ORAM controller kept in the enclave, which protects the access pattern between the trusted and untrusted memory. So researchers have been implemented path ORAM and circuit ORAM algorithms to protect the access patterns of the SGX applications. So it has some specific contribution because it achieved the efficiency than the classical ORAM setting because it reduced the server client communication as the ORM controller kept in the enclave and which is itself in the server side. But still it has some limitation because the ORM takes the order of login operation to access each data block, which is still not efficient. Also, like it only protects a set of data accesses when you have some data in the untrusted memory and you are accessing from the enclave. So this interaction between this set of the common set of data access only protected by the ORAM. It cannot protect the application-specific code access, such as the conditional branching in the enclave. Our observation is ORAM incurs high computational cost. If we can regulate the data flow of SGX application, it can be more efficient than the ORAM primitive. Interestingly, some application-specific access pattern does not leak additional information. For example, sequentially access the entire dataset doesn't leak additional informations. But still, there are other access patterns which can be replaced with the specific oblivious algorithms, such as the oblivious sorting, oblivious merge, and swap, etc. But to do that, there are a few challenges because you need to analyze in detail for each application specific access patterns, which is very time consuming and also error prone if you want to do it for every applications. Our contribution. We reduce the application-specific access patterns to a few shared access patterns by regulating the data flows with MapReduce. By utilizing MapReduce, we can also cover a wide range of data analytics applications where by protecting the access patterns of MapReduce, we can also protect a wide range of data analytics applications. And SGX MR, we designed a robust mitigation methods to prevent the untrusted memory access pattern leakages and also the in-enclave memory access patterns. We implemented the lightweight SGX MR framework, which is very flexible to adapt the enclave restriction, for example, the limited memory. And finally, we conducted extensive component-wise experiments to understand the cost and the performance of SGX MR, and we compare our results with the ORAM-based SGX approaches. Finally, we understand that the SGX MR can be several times faster than our ORAM-based solutions. Here we can see high-level design of SGX-MR, we divide the framework into two parts, that is the trusted part and the untrusted part. The untrusted component contains the small initiator program that starts the SGX-MR and also the encrypted files and the data blocks. Enclaves holds the rest of the components of SGX-MR, where the MR controller manages the data flow between the enclave and the untrusted memory. It only accesses equal sized blocks either sequentially or using oblivious algorithm to access the untrusted memory. And also the user-defined functions such as the mapper, combiner, and reducer also executes in the enclave. In the figure, we can see how we are regulating the data flows of SGX-MR. So it has basically three main phases. So the map phase, the sort phase, and the reduce phase. So in the map phase, if we see in the figure, it read the blocks sequentially and perform the mapping task and send the result to the combiner. When combiner receives the data, it aggregates the output of the map and sequentially writes the block to the untrusted memory. When the map phase is done, then the sort phase starts performing. So it sorts the mapped and combined output and read and write the data blocks to the untrusted memory. And at the end, the reduce phase performs as same as the map phase. It sequentially read the sorted blocks and aggregate the group-wise results, and finally sequentially write the blocks to the untrusted memory. While regulating the data flows of the SGX-MR, our analysis shows that there are multiple critical sections that leak sensitive informations. Some of the key information leakages are that there are leakages in merge sort. While performing the merge sort, the relative order between the records can be leaked from the block access patterns. And then there are the reduce phase leaks the group size of the aggregated results. And also, if we see, there are in-enclave access patterns that leaks the data-dependent branching from the enclave. The operating system can observe the page access patterns to find out the data-dependent branching. So we have analyzed each of the leakages and proposed the mitigation methods for each of them. Mitigation methods. We replaced the merge sort with oblivious sort. We adopted bitonic sort because it provides the identical access patterns irrespective of nature of the dataset. Although bitonic sort incurs a significant cost because the complexity of the sort is n log square n, which is log n times slower than the traditional merge sort. To protect the in-enclave access patterns, we leverages the oblivious operations even in the enclave. We apply oblivious swap, copy, and oblivious merge to protect the in-enclave access patterns. Also, we made the block level combiner mandatory to protect the group size in the reduce phase. Finally, the synergy of the curated components hides all the access pattern leakages efficiently. So we protect the relative order by protecting the sorting. We protect the in-enclave access patterns, and also we protect the group size of the reduced phases. For experimental evaluation, we implemented the prototype of the SGX-MR. The entire framework we have written in C++. The core framework written within the 2000 lines of code. And also the entire framework runs in the enclave except for the starter program. We implemented the custom bitonic sort that adopt the block level operation and also covers all the proposed mitigation methods. And also we leverages the CMOF instructions for conditional swaps and the sensitive branching patterns. And finally, we relies on the 128-bit AES counter mode encryptions from the SGX SDK. We experimented SGX-MR with two applications, the word count problem and the K-means clustering. To compare the baseline version, we compare our result with the ORM-based approaches. We applied the ORM integrated merge sort with the CMOF protection. We utilizes the zero-trace ORM implementation, which is the fastest SGX-based ORM. Experimental results. Here we want to show that how you're protecting the group size in the SGX-MR. In the left figure, we're showing the word count problem, the observed frequency versus the actual frequency. The x-axis is the top 100 words ordered by the actual frequency, where the y-axis is the word frequencies of the actual frequency and the observed frequency. If we see that, we can find we can observe that there is no relation between the observed frequency and the actual frequency, and the observed frequency from the reducer comes completely at random. And in the right side, we see that the k-means clustering, the cluster size is in the y-axis in the logarithmic scale. We see here also we see that the observed size is actually completely identical, so that the attacker cannot be able to distinguish the cluster size from the k-means clustering algorithm. Finally, the application-based evaluations. In the left side, we have shown the word count problem, and in the right side, we show that the k-means clustering. For both of the graph, we have compared the SGX-MR with the ORM-based implementation. So we can see that in the both graph, we see that the SGX-MR performs several times faster than the ORM-based implementations. And also, if we increase the data size, the ORM bar will go higher than the current version. So to sum up everything, SGX-MR avoids the expensive ORM as the block input-output operations, and it also avoids the error-prone application-specific design of the access pattern protections. It uses the MapReduce to regulate the data flows. It protects a large class of the data-intensive applications, and it addresses both the access pattern attacks and the page fault attacks. Thank you.